Let's revisit this topic of standard states one more time. Now, I mentioned at the end of the last lecture that biochemists have a tendency to redefine their standard state free energy, delta G naught, to be delta G naught at pH 7. And this has, there are reasons for this, which is that most of the biochemistry we're going to care about, at least as it pertains to living systems, happens around neutral pH. So we tend to like to think about things, excuse me, at neutral pH. But this also has implications for reactions or for chemistry when protons are a reactant or a product of the reaction, right? So as an example of that, consider the following reaction. Specifically, consider the effect of pH on the hydrolysis of ATP, which is something we just talked about with respect to that first critical reaction or acritical reaction at the beginning of metabolism, that formation of glucose 6-phosphate, which requires ultimately hydrolysis of ATP. So if we write out that reaction, right, fully, it would look something like this. So we'd have ATP 4 minus plus water would yield ADP 3 minus plus HPO4 2 minus plus a proton, right? So we can also write out, as we saw last time, the full expression for the free energy of this reaction. And it would look something like this, where delta G would equal delta G naught plus RT natural log of the concentration of ADP times the concentration of inorganic phosphate times the concentration of protons divided by the concentration of ATP times the concentration of water, right? Because water is a reactant in this reaction, this hydrolysis reaction. Now remember that what I've written out here is the free energy for the hydrolysis of ATP under an arbitrary set of conditions, not at equilibrium, right? So the concentration terms, or the activities in this expression, remember, are under any arbitrary set of conditions that I chose to try and calculate the free energy, right? Okay, because at equilibrium, the free energy change when the reaction is at equilibrium is that delta G naught term. But we're going to throw in a wrinkle, right? And the wrinkle in this case is what happens if we're going to carry this out in dilute solution I should say aqueous solution to be strictly correct. Dilute aqueous solution at pH equals 7, right? Now think about that set of conditions for a moment with respect to that expression. There are two things in that expression that under those conditions are no longer variables. Specifically, in dilute aqueous solution, does the concentration of water ever change? No, right? It's going to be that constant 55 molar. And at pH 7, if you're buffered at pH 7, is the hydrogen ion concentration changing? No. So under those conditions, both, well, of course, water, concentration of water and the hydrogen ion concentration aren't variables anymore, in which case we can now rewrite this expression to look something like this. So delta G, again, equals delta G naught plus, and now I'm going to use the law of logarithms to split that expression apart a bit. group these terms in a slightly different way. Log concentration of ADP 3 minus concentration of inorganic phosphate divided by the concentration of ATP plus RT log of principal, the hydrogen ion concentration. But if we're at pH 7, we know what that is, right? The hydrogen ion concentration at pH 7 simply has to be 10 to the minus 7, right? Divided by 1. Now, wait a minute. You say, wait a minute, wait, Dr. Rye, wait. Why 1? Where'd the 1 come from? Remember, I split the two things out of that expression that are no longer variables: hydrogen ion concentration and water. Hydrogen ion concentration is clamped at pH 7, right? So 10 to the minus 7 by the fact that I'm buffering at pH 7. And remember, again, that these are technically activities, right? And at 55 molar dilute solution where water doesn't change, its activity is 1, right? Okay, so that term now, this term is a constant. And I can fold that constant into my definition for the standard state free energy. Doing so, I can rewrite this expression, or I can define a new standard state free energy that looks like this, where delta G naught, and there's the prime, is simply equal to delta G naught under normal standard state conditions, 1 molar and everything else, plus RT log 10 to the minus 7th, right, over 1, or just 10 to the minus 7th. And I now have a new definition for my standard state free energy, all right? And I can now use that to write out the expression for the free energy change of ATP hydrolysis at pH 7. So it now simply equals, or I just add my prime there, delta G naught prime plus RT log of what I had before, ADP times inorganic phosphate over the concentration of ATP, right? But now, what if I'm going to say, what if I do this at equilibrium? I should make one additional note here because I flipped some nomenclature on you here, right? So some of you may know this, some of you may not. That P sub I that I'm writing there, that's equivalent to inorganic phosphate, right? That's the same thing as HPO4 2 minus, right? It's just easier to write P sub I. Okay. So what about at equilibrium, right? At equilibrium, as we saw the last time, the free energy change would equal 0. So if we're at equilibrium in buffered conditions, right? Which now has to equal delta G naught prime plus RT log, where we would now at equilibrium be at the equilibrium concentrations of these substances at pH 7. Right? Which simply means, as we've seen before, delta G naught prime is going to equal RT log of the equilibrium constant. And technically, you would add a prime there as well to indicate that you're at pH 7, though most biochemists doing things like this, the neutral pH is usually implicit, and you don't usually see people put the prime there. But formally, using the nomenclature I'm using here, that would be consistent. So that then gives us this new definition of delta G naught with the explicit statement of the free energy change for a reaction at pH 7. Okay.